Hey, hello friends, welcome back to the channel. This is your friend Aili Bhattacharya, your stats buddy, and today we are going to cover one of the most important topic of our syllabus, which is regression. So let's start from the next slide. Yes. So by regression of a variable y, say on another variable x, say, we mean the dependence of y on x on the average. Okay, starting simple, regression is just a fancy word for dependence. It's how one thing y depends on another thing x on average. Not an exact rule, but a general trend. Like on average, the more you study x, the better your score is y. Next line, in bivariate analysis, one of the major problem is prediction of the value of the independent variable y when the value of the independent variable x is known. See, bivariate just means two variables, and the main goal here is if I know my x, how many hours I studied, I want to predict my y, what my test score will be. That is the whole point. The problem becomes simplified if we can express y as a mathematical function of x. Y is equals to hx, say. Then this equation is called the regression equation of y on x. So instead of guessing, we want a formula. If we can write y as some function hx, that formula is called the regression equation. It is our prediction machine. In the simplest case, when y is linearly related with x, either exactly or approximately, we can write y equals to a plus bx. And the simplest function of all, a straight line, right? We all know the line equation, which is y equals to a plus bx. A is the y-intercept where it starts, and b is the slope, how steep it is. This is linear regression. So, for example, if I say that if b is 5, it means for every 1 unit increase in x, y goes up by 5. Now, see, coming to the next slide. Yes. See, the constants a and b have to be estimated on the basis of observed values of x and y. Suppose we are given n pair of values xy, yi. See, here's the key. We don't just guess a and b. We have to calculate them based on real data we have collected. So we have n pairs of data points. For example, from 10 students, our studied and test score. Okay? So this is our example. Now see, when x equals to xi, the observed value of y is yi and the predicted value of y is a plus bxi. So ei is equals to yi minus a plus bxi, which is the error. The method of least square requires that a and b should be so determined that summation ei square is a minimum. See, this is the most important topic of our class. See, for any student I, our line predicts a score, but their actual score might be different. The difference is the error, which is the EI. Now, we can't just minimize the sum of errors because positive and negative errors would cancel out, right? So, we squared them first. The least square method finds a unique line that makes the sum of these squared errors as small as possible. It is the best fit line. See, we are literally finding the line that's on the average, closest to all the data points. Okay? Now, coming to the next slide. These are called the normal equations. First, you see that summation yi is equals to na plus b summation xi. Number two is summation xi yi equals to a summation xi plus b summation xi square. By using calculus to minimize that sum of squared errors, we derive these two equations. They look scary, I know that, but they're just two equations with two unknowns, a and b. Okay? We plug in our data sums and solve for a and b. This is the math behind the magic. Okay? Now see, from 2, we get y bar equals to, from 2 you can see here, y bar equals to a plus bx bar, or a equals to y bar minus r sy by sx x bar. See, look at this cool, very cool result. The first normal equation simplifies to show that the regression line always passes through the average of your data, the point x bar y bar. This is a huge insight, right? Your line of best fit always goes to the center of your data cloud. Okay? Now, substituting the estimates, we get the linear regression equation of y as y equals to y bar plus r sy by sx x minus x bar. After all the algebra, we get this beautiful final form of the regression equation. So let's break it down. It starts at the mean y bar. The slope b is now r into sy by sx. X minus x bar is how far x is from the average. So your prediction starts from the average y and then moves up or down based on how far your x is from the average, right? This is scaled by the new slope. Now see, coming to the next slide. Yes. The quantity R Sy by Sx, usually denoted by Byx, is called the regression coefficient of y on x. It gives the increment in y for unit increase in x. This is the official definition of the slope, right? See, Byx is the regression coefficient. We already learned that. If Byx is minimum, or not minimum, if Byx is 5, it means for every 1 unit increase in x, we predict y will increase by 5 units. It is the engine of your prediction, basically. Okay. Now, see, it may be noted that there is another regression line, the regression line of x on y. See, there is a plot twist. There isn't just one regression line, there are two. We have been looking at y on x, which predicts y from x, but you can also flip it and predict x from y. That is the regression line of x on y. Okay? Now, see here. See the graphs. The quantity R Sx by Sy, usually denoted by Bxy, is called the regression coefficient of x on y, and it gives the increment in x for unit increase in y. See, for the other line, the regression coefficient Bxy is R into Sx by Sy. It's literally the flip of the other one. It tells you how much x changes for a 1 unit change in y. Okay, see the graph here. First graph here shows the regression line of y on x and the error. Here is the error. And see this graph, regression line of x on y and the error. This is the error. Okay, now coming to the remark. Here is the remarks. What are the remarks? First, the two regression lines intersect at x bar and y bar. See, the key fact is both regression lines, no matter what, will cross each other at the center of your data, which is the point, that is x bar and y bar. So there it is, right? Like they always meet at the mean. Point number two, the two regression lines are usually different because they are derived under different conditions. In getting the regression line of y on x, we minimize the sum of squares of the errors of estimation of y, while for the other, we minimize the sum of squares of errors of estimation of x. See, why are they different? Because they are minimizing error in different directions, right? X and y, all right? See, y on x minimizes the vertical distance error, errors in predicting y. X on y minimizes the horizontal distance error, errors in predicting x. See, they are solving two different problems. So they give us two different lines. The two lines, however, coincide when r equals to plus or minus 1. Here is an interesting part. When do they become the same line? Only when the correlation is perfect. When r equals to plus 1 or r equals to minus 1, all the points fall perfectly on a straight line. In that perfect case, there's only one line and both method finds it. And that's it. By breaking it down line by line, we have conquered linear regression. So if this video helped you, smash that like button and subscribe for more textbook deep dives. Let me know in the comments which other topics you would like me to explain. So, yes, now time to say goodbye. See you in the next one. Study hard. Exams are coming, right? So, yeah. Bye bye. Thank you.